Should we get started?
Sorry for you guys. I pity you.
Maybe we can get started.
Yeah.
There
Can
are
you hear me?
104 participants.
Okay.
So, hi everyone, welcome. I'm Ken Interrogator from UC San Diego, and I'd like to start off by thanking the fellow co-organizers and our speakers. Many of us have been to and enjoyed different summer schools like TASI and others, and we hope that you'll enjoy this one too. Clearly it'll be a different experience, but one of the great things about these summer schools, in addition to hearing from great lecturers at the kind of forefront topics, is meeting fellow students. And so we hope that you'll have opportunities to meet some of the fellow students. One way to get to know each other might be to send questions or comments in chat. And then also we have this gong show and poster possibilities. And maybe you can also organize some of your own ways to interact with each other. Let's see, should we have the different co-organizers introduce themselves? So maybe Ibu?
Hi, so I'm Ibu. I'm at Johns Hopkins University. I sort of mainly would be running the Zoom setup. So it's set up to run from 9 a.m. to 4 p.m. Eastern time. And during that time, there are lectures, there are various things happen, but I'll try my best to keep it as open as possible if you guys want to log in and talk to each other and interact. And if you have questions, I guess you can just either send it to any one of us and we'll try to answer.
Let's see, maybe Jonathan?
Hi, I'm Jonathan Heckman at University of Pennsylvania. So I'm just looking forward to the lectures. That's it.
And Sarah?
Hello, so I'm Sara Pasquetti from Milan Bicocca, and thank you very much for joining us in the school, and feel free to email me if you have problems and I can be of any help.
And Shlomo?
I'm Shlomo Razamat from Technion, so thank you for participating, and thanks everybody who signed up for the Gong Show. So I'm looking forward to that. So as others said, if you have any questions, feel free to send me anything. Thank you.
And Sakura?
Hi, I'm Sakura Shafan-Amiki. I'm normally in Oxford. At the moment, I'm in London. I'm mainly also responsible for the web page, that everything is posted there correctly. So if you have comments there, just send me an email. And thanks for signing up, and hope it'll be exciting to talk about physics in the next 2 weeks.
And Alessandro?
I am Alessandro Tomasiello from my kitchen in Milan. I'm very happy to see that many gay people have come to this, have chosen to register to this school, and I'm looking forward to the lectures. And if I can help in any way, feel free to write to me.
Okay, so our first lecturer is Kantaro Ohmori, who posted his lecture notes on chat, and also will be posted on the website. And I had a very enjoyable time meeting or getting to know Kantaro in Aspen, and he's an awesome skier. So maybe go ahead and start, Kantaro.
Okay, yeah, thank you very much for the giving me this great opportunity to give the lecture. So I mean, this is my first lecture, the very first lecture to give. So I hope I try, and I hope I will succeed. So the topic, I mean, I a bit changed the title, and the title will be Anomaly and Topology. The original title was something like the topological phases and anomaly, but I found that I'm not going to talk very much about the topological phases. So, but I will still talk about the topology. So I changed the title, and yeah. So let me explain how the things will go. Here, I posted the 2 PDFs. One is the Leg 1 PDF, and the other is the Leg 1 incomplete PDF. And I'm opening the incomplete one, which means that there's some blank in the note. And if you open the complete one, everything is written. So if you want to go back and to look at, you can do that. But here I'm just going to write in something here. Okay, and so that's how it will go. Okay, and okay, so first, before starting, I will just summarize what I'm gonna do. So in the lecture one, I will just give the modern overview on the topic of symmetry and anomaly. And unfortunately, I don't know of any good, any review on very modern point of view of this. So I just listed the two lectures given by my long-term collaborators, Yuji Tachikawa with my advisor actually, and the Kazuyane Kura. Okay, so these two lectures are both very good and huge overlap with mine. Okay, so you can look at, and also yeah, and original papers. Yeah, original papers are like this, but mainly these papers are mainly about the cobalisms. I'm gonna give other references on the way. And the lecture two, I will give. So lecture one will be very abstract and very broad. So I hope that in lecture 2 and 3 we can do more concrete things. So in lecture 2, I will first talk about the fermions, anomalies of the fermions, pre-fermions, and also the 6 SCFTs. Hoping that will help the other lectures by other lecturers. And the lecture 3, I want to, if I have time, I want to talk about some very nice paper by Gayato Kapustin Commodity Dialogue on the YAM mills, for the pure YAM mills, non-supersymmetric. And so you can, yeah. And so they, yeah, so that's my goal. And the disclaimer, I will not be able to give a correct and thorough list of references. So this topic is very old, obviously, and it's like, for me, it's like many works are done before I was born. So it's very hard for me to give correct original references. I try to give useful references for the recent references, but I will just say we'll fail to honor the old original references. And yes, and obviously most of the lecture is not by me, so that's obvious, but I'm just saying. And a small remark is that in this lecture, if someone in the condensed matter background is hearing, in this lecture, D means the space-time. So this word is 4D, and okay. So that's the HEP-TH convention. Okay, so let's start. Is there any question on this page? Okay. So first I will, yeah, so, okay. So on this lecture is, first I briefly talk about why we care about the anomaly and symmetry. Then I will briefly introduce the overview of the symmetry and overview of the anomaly and its relation to topological phases or topology in general. Okay, so why symmetry and anomaly is important? And that's what, because they are RG flow invariant. Okay, so if you have some UV theory and the flow, RG flow to the IR, so here, yeah, assume that we have in UV some group GUV and its anomaly, fifth anomaly AUV, and in the IR we also have some symmetry GIR and its anomaly AIR. So these two have a very concrete relationship, and here GUV and GIR are assumed to be faithful. So the faithful means that you have, for any element in the group G, there is some operator in the theory, and such that the group element acts non-trivially on that operator. Depending on who you ask, maybe someone imposed that this operator has to be local, but here I'm not imposed that. Well, there's some subtle variance of the definition, but it doesn't matter in this lecture. Okay, so if this both the GUV and GIR, sorry, I failed to say that I really encourage for the students to ask questions. So in particular, this lecture will be, this lecture will be very abstract. So, and yeah, I think it's very important to ask questions. So if you have any, please interrupt me and at any time and ask questions. Okay. And so first, under the RG flow, the symmetry is preserved, and so concretely, it means that there has to be a group homomorphism from UV symmetry to IR symmetry. These are neither, not necessarily neither surjective nor injective, but there has to be a group homomorphism. Because I defined these groups to be faithful, so some UV symmetry might act trivially on IR, so some degrees of freedom decouples, and it happens that also there can be emergent symmetry in IR. So it's not surjective nor injective, but there has to be a homomorphism. And the anomaly, of course, I'm going to introduce it later, but the important point is that the anomaly is also should match the sense that if you pull back in the algebraic topology sense, if you pull back the anomaly, that should realize the UV anomaly. Okay. At this point, you only have to know that there is a concrete relationship between the IR anomaly and the UV anomaly. Okay. And so there are two important use cases. One is when UV is weakly coupled. Okay, so in this case, okay, so such case is typical in the dimension lower than 4. Like just think about the gauge theory with the weak coupling in asymptotic free gauge theory in UV. In the IR, it's strongly coupled. So you cannot do the direct perturbation theory in IR. But still, the important point is that this anomaly gives some information on the IR, even if it is strongly coupled, because of this equation. So in other words, this anomaly constrains the IR physics. Okay, so that's one typical case. Another is just opposite. In higher dimensions, it's often that IR, often we consider IR free theory. So IR is weakly coupled. Okay. So in this case, just we get the constraint, or at least, or know something on the UV theory. Okay. So in higher dimensions, higher dimensional superconformal series, in particular in 60, the UV theory is some mysterious strongly coupled theory coming from string theory, but often the IR is just a weakly coupled gauge theory. The IR effective theory look like a gauge theory. So in that case, we can compute the anomaly from the IR point of view. So that will be a lecture. Okay, any questions? Oh, so this is one reason, and another reason. There's another reason is that we can, if we have symmetry, we can just do gauging. Okay, and so gauging is important because the gauging some symmetry of the given theory gives a new theory. And also this gauging gives the relationships between the theories. Okay, and so this gauging, in other words, the gauging organizes the space of the theories. However, gauging is not always possible, and this the fifth anomaly, or quantum anomaly, is the obstruction. So anomaly gives the obstruction to do gauge. Okay, so these are very broad reason why we care about the symmetry and anomaly. I briefly mentioned that the recent progress in this decade, and this decade, I think we can there are two main points where we made progress. One is that the discrete symmetry. Discrete symmetry and non-perturbative anomaly. So of course, from the 80s, the anomaly have been studied, symmetry and have been studied, but mostly on the continuous symmetry and perturbative anomaly, with the great exception of Witten's global anomalies. And recently, inspired by condensed matter physicists, the VQFT people start to think about the discrete symmetry and more general non-perturbative symmetry involving both discrete and the continuous symmetry. And it turns out that it gives us very abundant information on the strongly coupled QFT. Okay, so that's one progress. The other is the generalization. So generalization of the notion of symmetry. So here, about this, I will talk more about later. But yes, so these two are the important points. And okay, so now I'm gonna talk about the symmetry in more detail. Any questions so far? Okay, good. So, okay, so symmetry. So first, let's remind ourselves of the continuous symmetry. So if you have some theory with some continuous symmetry, here I'm talking about the global symmetry, then we have a current operator, usually called J mu, and you might have some index A in the group algebra. So this is values in some Lie algebra, and the mu is of course a space-time index, so this is a vector. Okay, and so of course the current should obey the conservation law. This is conservation, but it's classically, and it's convenient to define this d-1 form operator just like this. So okay, so if we define d-1 form operator like this, just the definition of the current, then this conservation law means that this current, oh sorry, yeah, I said something. Let me here just assume the this is U1. Yeah, I wrote something wrong. Let me just assume U1. Then okay, so then this is the conservation law. It just means that, yeah, just use a the close. Sorry, yeah, I failed to get that. Of course, if it's not variant, that should be the covariant derivative. But yeah. Okay, so just use A's, and okay, so given the current operator, we can define the charge operator Q, and that's just the integration of this d-1 form on the time slice over the time slice. And the conservation law means that this Q is preserved. Okay, so this is very standard thing, but from the modern point of view, we can just think about the charge operator on any codimension 1 surface in the spacetime. Okay, so this is sigma d-1 is any d-1 dimensional submanifold on your spacetime, and you can just integrate J over your codimension 1 surface, and then because J is closed, so this is topological. I mean, oh yeah. So because if you slightly modify your sigma d-1, still it's because the J is closed. So as long as this sigma d-1 doesn't cross any operator, the value of Q doesn't change. Okay, and it's okay. So this is also, I think, standard. Yeah. So here, just for simplicity, I don't want to just. Also in U1, so I changed everything to be U1. So it's convenient to define U instead of Q. So this Q still takes value in the Lie algebra, but to generate the discrete symmetry, it's more convenient to define something value in the group. Okay, so to define it, we just exponentiate. So for U1, so for some phase, U1 phase, we define corresponding to each U1 phase, we just define U to be the exponential of Q. Okay, and so in particular, Q actually so in particular, so something this is in integer. So Q is in integer, also integrating, and sorry, I said something wrong. So then this is in U. Okay, so yeah, sorry for saying something wrong. Okay, so this, as I said, this UG generalizes to the discrete symmetry. And so for discrete symmetry G, like some Z2 or Zn, or more generally some maybe the non-abelian finite group, there's no current operator J because it's discrete, but still we have, as I said, the topological operator UG. Topological. Okay. And also codimension 1. It still defines on some codimension 1 surface. Okay, and this UG should respect the group multiplication law. So if you have some UG1 and UG2, and you can just smash the two, and you should get UG1, UG2. Okay, so this smashing operation should be just group multiplication law. And
Kantaro, there's actually a question in the chat by Shin Toida. And he's asking, or they're asking, are you caring about the global structure of the symmetry group?
Yes, I mean, ultimately, yes. Good question. So in discrete symmetry, there's only global structure in a sense. In continuous symmetry, yes, this U should value in the group. And yeah, when you carefully analyzing the system and symmetry and anomaly, yes, in general, you should care about the global structure. Yeah, that's another point that the people only recently start to care about. Yes, that's a good point.
Is there a difference between a Euclidean signature and a Minkowski signature? I mean, yeah.
Here, as far as what I am currently talking about, no, this should work either way. But in this section, what I have in my mind is Euclidean signature QFT. Yes, but it should work anyway. Yes. About this, the topological operator should work even in Minkowski space. Yes. Good. So I was talking about the topological operator UG, and so yeah, and one important thing is that if you have these topological operators corresponding to the groups, there should be some junction. So if you have 3 operators, UG1, UG2, then UG1, UG2. So this is just a group multiplication, and when these three are consistent with the group multiplication, then you have one-dimensional space of the junction operators. Okay, I mean just the single junction operator. Okay, and yeah. So, and this UG topological operator acts on other operators, say local operators. So if you have some local operator, and if this topological operator U pass through the local operator, this symmetry should act on the local operator. In other words, you should get G acting on this local operator O.
Kantaro, you are drawing the arrows. Can you comment on what they mean?
Oh yeah. In general, the orientation of the surface matters. So yeah. Arrow means, well, you don't have to care in this lecture, but in like yeah. But surface should carry the orientation. So it's like, and if you have opposite orientation, it's like inverse.
Thank you.
That's clear.
Yes, thank you.
Okay, so well, one example of the discrete symmetry is, say, if you have real scale phi, then obviously you have I mean with some symmetric potential, you might have the C2 symmetry flipping the sign of the real scale. Okay, so this is example of Z2 symmetry, and so in that case you have this corresponding topological operator. In this case, just one non-trivial topological operator for Z2, and if you have if you have the scalar field phi, and if you pass through the topological line, you get the negative of the scalar field. Okay. So this is the meaning of the topological operator. Okay, so this is topological operator. And if you have a symmetry, then it's very convenient to think about the background that couples with the symmetry. So for the continuous case, this background is the G connection on your space-time manifold M. And so this is the locally some one form valid in G. And and the introducing background means that your partition function depends on the connection. Here I'm not gauging, so I'm just putting the background A. That's not dynamical, but you mean what you do is just covariantize your derivative, and usually, and if you expand the action, it's you have this linear term in A and possibly a higher term. Okay, so this is the coupling to the background in the continuous case. And even for the discrete case, we can do something similar. So there's a notion of the G connection even for the discrete symmetry called the cocycle. This is one cocycle. If you are familiar with some simple shell or some homology theory, then yes, this is the one cocycle, and G value is one cocycle. But more intuitively, I'm not going to explain what the cocycle is, but it's more intuitive to think about its Planck ideal, which is the insertion of the network. What? Network. What? So network of the topological operators. So inserting some background for the discrete symmetry is like, in general, inserting some network of the topological operator. So as I said, you have some junction between the topological operators U. So you can draw some arbitrary networks on the manifold like this. Okay. So that's the meaning of the coupling to the discrete symmetry background. Yes. So yeah, even in the continuous case, of course, if you also think about net insertion of a network of the topological operator, even for the continuous case, but such background only corresponds only to the flat background. So if the symmetry is continuous, there's also the non-flat background. So the covariantization is the more general coupling. But if the symmetry is discrete, there's no way to have a non-flat background. This is a technical remark. So yep. So for example, if the symmetry is just a Z2 and your manifold is a torus, then you can so the background is equals to inserting some network of the topological operators, but for the Z2 there is not so many possibilities, so you can just insert a Z2 line like this, or like that, or like that, like that. Like, of course, there are infinitely many ways, but those are all of them corresponds to the Z2 background. Okay. Is this clear so far?
Question in chat. In the real scalar example, can we express the Z2 operator in terms of the scalar field? Like in U1 case, we write down the current and charge explicitly in terms of the fundamental fields.
Good question. Missing. Yeah, kind of guess so. Yeah, you can just treat it as if it were complex, and then you draw U1. You can just write down the U1 charge operator, then just pick the phase to be -1, and that should work. Am I right? Yeah, I guess so. Yes, this should work.
Another question in chat. Is the fusion of the topological operator always compatible with the transition function of the atlas? Or do we have non-trivial consistency condition with coordinate transformations?
Good question, I guess. Here, I was assuming that the group is not interact with the space-time. In that case, I mean, like the V2 of a scalar field, yes. In that case, these are just topological, and you don't care about the coordinate transformation. But more generally, like if you consider the spin structure, or I mean -1 to the f, or like that, or even if you care about the time reversal symmetry, then those are the space-time symmetry, discrete space-time symmetry, and also other symmetry can have some non-trivial relationship between the space-time symmetry. So in that more intricate case, yes, it can interact with the space-time structure. Yes. If reversing the orientation amounts to changing the group element with its inverse, does it mean that every topological operator has an inverse? Yes, that's very good question. Sorry, and so here, of course, yes. Sorry. Yes, for the group symmetry. So as long as you're considering the topological operator corresponding to a conventional sense of symmetry, yes. So, but this relationship is only true for this kind of operator corresponding to the symmetry, and it's not always true. And I'm gonna comment on that. Yes. So there are non-invertible lines, and so still there is a dual, but it's not necessarily the invertible. Yes, I will comment more on, I mean, soon. Okay. So yeah. So I want to talk about the generalization of the notion of symmetry. And so first, as I said, the continuous symmetry corresponds to the vector field. Field with one index and just the conservation law. You can also try to think about some operator with more index and with some conservation law like this. Okay, and so and we can also impose some symmetric or antisymmetric property in these indices, but it turns out that in non-free theory, I think, I'm not sure this is a theorem or not, but usually in non-free theory, we only care about the case that all the indexes are totally antisymmetric. And yeah, of course, in abstractly, there might be other operator with other symmetry property, but I think those are constrained to the free theory. But I'm not sure that's proven or not. And okay. And so for this case, if the indices are all totally antisymmetric, do you care if the condition one surface is compact or not? You can consider either. Yes. Okay, so in this case, called, so such, having such operator is called the continuous higher form symmetry. And I think first, the notion itself is first introduced by the, don't want to miss this paper, the Gallardo-Kapustin-Zaropiret, and okay, and okay, so this is for the continuous higher form symmetry. There is also the discrete higher form symmetry. So that corresponds to thinking about the topological operator for each element of some discrete group. But yeah, oh sorry. So the conventional discrete symmetry corresponds to the topological operator of codimension 1, and it's invertible. As I said, because you have for any element G, you have G inverse because of the definition of the group. So like this, and also this UG it should be topological. So you can just relax the condition to generate the notion, and so one way to generalize is that the discrete higher form symmetry which corresponds to the codimension P greater than 1 and still invertible topological operator. Okay, and another way of generalizing the notion of symmetry is just thinking about the general topological operator. Either any codimension, and you don't care whether it is invertible or not. So in some case, there are topological operators, but that doesn't have any inverse. Okay, so such notion is called, I call it the category symmetry. Shalom may call it the categorical symmetry, and other names by used other authors, but that I think that's the most general generalization we are thinking. Okay, yes, I would, if we want, I want to talk more about this category symmetry in the discussion session, and I preserve it to there. Okay. I'm so sorry that my computer is running out of battery. So I have to, I send back, sorry. Sorry, I'm back. Sorry for the disruption. Any question?
Is there a well-known mathematical structure associated to what you described in terms of assigning basically a representation of your group to each codimension 1 surface of your ambient manifold?
Sorry, I couldn't get the question. Here, I assign not the representation, but the element.
But you have a symmetry group, right? And the idea is that you're assigning a group element to each codimension 1 surface for arbitrary group elements, and it has to be compatible with the group multiplication law. So is the idea that you're assigning a representation for each codimension 1 surface of your group, or is that not accurate?
Here I'm not talking about Wilson lines. Here I'm just after gauging of, if you're concerned with gauging some symmetry, then after gauging you can think about such Wilson lines. But here I'm assigning the elements, not the representation.
Okay.
Yeah.
Oh, that's.
Yeah. Okay, so anomaly. Okay, so then I go to the topic of anomaly. 5 pages, so it's slow. Okay. I can get. So, okay, first I have to introduce a gauge transformation. So if you have for the continuous symmetry, you have the connection A, and the gauge transformation law of the connection is like this. Okay. Here the G is the gauge transformation parameter, so this G depends on your position of in your space-time manifold. And for discrete gauge for discrete symmetry, if you are treating the background to be the Wanko cycle, then yes, you can just do the same. If you know the notion of the homology complex, but it's more intuitive to think about the topological operators. So, well, technically, it's going to be useful to think about this formal thing, but intuitively, it's more good to think about the topological operators. So this kind of gauge transformation corresponds to just the topological move of your topological surface, and also some kind of the recombination of the junctions. Okay, so in 2D, well, it is generalizable to higher dimensions. For explicitity in 2D, so you can have this kind of two pairs of the junctions. Then you do flop. So these external group elements are the same, but you can just flop here to there. So combined with the general topological moves, this constitutes the gauge transformation of the discrete symmetry background. Okay, so these are gauge transformation of the background, and so anomaly is simply so we can ask that whether the partition function is independent of this this gauge transformation. Okay. And the answer is no in general. No in general. And the most well-known phenomena is the perturbative anomaly. So when G is continuous, so that, for example, for the U1, and if you have chiral fermion, this is chiral fermion. It's just a free chiral fermion, but with a wire fermion with the U1 symmetry acted on it. Then there's a perturbative anomaly coming from the one loop, and that means the conservation law, if you have a background, the conservation law is modified like.
Kantaro?
Yes.
There are a couple of questions in chat. So one is, in the picture on the left, are we merely deforming a topological operator so the gauge transformation amounts to no change in the system at all?
Yes.
And also
yes.
about what the flop is referring to.
Okay. So, this is trivial. I mean, by definition, I said it's topological. So, yeah, I mean, obviously, this does nothing. And so for this type of move, I'm just to be complete. So one, I mean, this is like you can say that this move is trivial, and what's important, what's interesting is this. Okay. And the other question is what's the flop? So yes, sometimes I call this move to be flop in 2D. Just I mean, like the recombination of the junctions. Just the name I'm using. It's probably not very conventional. If you have a network of topological line, then I mean this move does nothing. This move does nothing, but this might do. I just said that this is a gauge transformation, and so the question is that whether that gauge transformation do something or not. Okay, so I'm going to talk about that. Jonathan's question is very precise. Thank you. Jonathan's answer is very precise. Thank you. Yes. And so going back to the anomalous conservation law. So if this F is just the usual field strength. So if you turn off, if you don't have any background, if you turn off the background, then this is still conserved. The J is still conserved. So the symmetry is conserved with that background. But if you turn on the background, there with anomaly, you have some mild violation depending on your background. Okay, so this is the meaning. If I use the form, it's just the J equals to proportional to FHF. Okay. So this is a U1 perturbative anomaly, and so if you have that, then so if you do the gauge transformation law, because of this coupling term, you get some phase. Maybe lambda is the parameter, transmission law parameter. So this is the anomalous space. The point is that it's not the arbitrary function. It's kind of fixed by the background and your gauge transformation parameter, and so in that case, say it's anomalous, but it's not wild. It's controlled in some way. Okay, and so this is the well-known perturbative anomaly. For the discrete symmetry, there can also be the anomaly. And so for the 2D, so this what I call the flop transition in general. So this flop transition depends on the 3 inputs, G1, G2, G3. By the consistency, the last one has to be the multiplication of the 3. Okay, so I might have some phase or in general some number if I do this a gauge transformation, and if this is not, oh yeah, okay, so in general I might have this and number, and so here, so in other words, alpha is some map from G cubed to U1 or U1, okay, and here I'm not assuming any compatibility with the group multiplication law. So this alpha is just a map between sets. Okay. Alpha doesn't care the group multiplication law so far. Okay. But this alpha should respect, how do we think of the flop or operation as the gauge transformation? Here I using this as here I'm using this as the definition of the gauge transformation. So yeah, and so of course you're asking that why this is the good thing to do. Yeah, so you can phrase the gauging of the discrete symmetry. Okay, here. So okay, so if you consider discrete gauging, there's in particular in 2D, it's often called the orbifold. And what they do in the 2D orbifold is that the summing over the network up to this flop transition. And so like in Z2, the orbifold is sorry for being small. Try to be more. This. And so the gauging, Z2 gauging is like this, that this means that you have Z2 holonomy in this direction. You have Z2 holonomy in the horizontal direction, and vertical direction, and both. Because but here by flop, this should be equal to inserting the Z2 line in this way. And because the holonomy is the same for these two, and yeah, so in that, at least in that context of the orbifold, yes, we only care. I mean, we are assuming that this Partition function with this background doesn't depend on the the precise network we are considering, but the up to the flop transitions. I hope this answers the question. Are there other canonical ways to generate a gauge transformation apart from a flop transition, or can you generate all transformation with flop? Yes, yes, this is the all. Into the higher the move, I mean, more higher dimensional move, but yes. Okay. Yeah. So yeah, so this alpha has to satisfy some consistency condition. So if we consider this network, so we have 3 lines coming from the below, and this is G1, G2, G3, G4 going out. This. Then if you go upwards, so first we do the flop here, we get there, and we do here. Maybe not. Yeah, right. Here, and if you do flop here, we get this picture. But we can go the other way. First we do the flop here to get there, and do flop here, and then do flop there. So there are two different ways to get to the same picture, and these two should be the same. Okay, this is the consistency condition to this alpha, and so if we explicitly write down, we can just so this is coming from this move, this coming from this move, and should equal to, if you go the other way, but we get so this is like G1 and G2, G3, G4, and G1, G2, G3. And so this is, and this, such alpha satisfying this equation is called the group 3 cocycle. In the math notation is like this. Okay, so in general, if you have some non-trivial solution to this equation, this should hold for any G1, G2, G3, G4. Yes, so counter and okay. Okay. So yeah. Okay, so this is a possible anomaly for the 2D discrete symmetry, but the anomaly suffers from the counterterm ambiguity, and the counterterm. So in the continuous symmetry case, you can, if you have some Gaussian function depends on your background, you might write some arbitrary local function of the background and multiply it to your original Gaussian function. And if you do such thing, that modifies the anomalous space. And it's often that there's no canonical way of choosing this kind of counterterm. it depends on your regularization scheme. So such a local counter term does not change the dynamics of the theory, because you're just writing a classical number in front of the original partition function. It depends on your non-dynamical background, so it doesn't do nothing. So, but it still superficially contributes to the anomalous transformation law. So anomalous phase. So that anomalous phase up to the counter term contribution matters. Okay. So if you absorb your anomalous phase to totally into some local counter term, then you don't care about it. Okay. So in the discrete case, the counter term of the discrete connection A is corresponds to the redefinition of the junction. So we have junction, but we can just modify junction by some phase. So that's the analog of the local counter term in the continuous case. And this modifies the junction. So if you consider this a flop, so flop flop transition, if we redefine the junction to this beta by this some number beta, then accordingly this alpha is modified by some delta beta, and this delta beta is just if you can just do this modification for this for junctions and correct it. So this will just be so the modification of modification of this alpha is like this. Okay. This and yeah, and this delta is called the co-boundary operation. Co-boundary operation. So if we care only up to of the alpha only up to beta, I mean delta beta, then actually that defines something called a group cohomology. So into the discrete symmetry G, anomaly of discrete symmetry G in a bosonic theory, so then we don't care about the fermions or the spin structures of the manifold, then up to the redefinition of the junctions, and so that's classified by so-called group cohomology, and the definition is just the usual cohomology here. The Z3 is the set of the three cocycles. So this is alpha, the pentagon, and here just the set of co-boundary of beta. Okay. So, and so this three is, of course, the alpha takes three arguments. And so there are, of course, this is just a third order group cohomology, and there's a generalization to a arbitrary order group cohomology, and this 3 is 2 plus 1. So in D dimensions, the anomaly of the discrete symmetry and in the bosonic theory is classified by the degree D plus 1 group cohomology and defined similarly. Okay. The pentagon identity becomes more complicated, and also the covariance operation becomes more complicated, but can be general. Okay, so I think I should finish. I should stop. So I just gave the exercise. Compute the this mean the 2D the classification of the 2D Z2 anomaly in the bosonic theory, and yes, and the hint is that so alpha is fixed value in the cube of Z2, so it's there are 8 possible arguments. It's a bit too much. So first, you should use the use the freedom of beta and the gauge fix, so that this alpha is 1 whenever this in the one of this at least one of the G1, G2, G3 is the identity in Z2. Okay. Also, you shouldn't be fooled by the notation. Here in this lecture, I haven't used this multiplication as a group multiplication. So if you're thinking about the Z2 to be the 0 and 1, then 0 times 0 is 0, the sign. But 1 times 1 should be regarded as 1 plus 1 equals to 0. So you shouldn't be fooled by that kind of notation, and not to be fooled by that. It's better to think Z2 to be the 1 and minus 1 to be the phase. Anyway, that's the comment. Okay, so this is the exercise, and I stop here and take questions.
Thank you, Kantaro. There was a question in chat about what the Wess-Semino consistency condition corresponds to in this case.
Oh yeah, so that's the pentagon identity. Yeah, great question. Yes. Yeah. So I didn't really talk about the Wess-Semino consistency condition for the continuous case, but yeah. So you can it's okay to think that this is this what corresponds to Wess-Semino consistency. Yes.
And
Other
there was another question in chat about what information is put on each junction, complex number sitting on the junction that we can scale by beta. What's the physical meaning of these numbers?
Oh yeah, so I mean beta is just the ambiguity. I mean, yeah, so yeah, there is no canonical way to fix the definition of junctions. So yeah, it's like the continuous case. For the local counter term can differ by your regularization scheme. So this definition of junction very much depends on how you define, and we can easily so the beta is just we can, beta rather represents the ambiguity of such definition. And yeah, so that's the meaning of beta. And so, and yeah, and the point is that we don't care about such, we shouldn't care about such ambiguity. Yeah, in other words, such an ambiguity is not the RG flow invariant. I might write beta to be depends on the scale. That easily breaks the RG flow invariance. But the point is the alpha up to such an ambiguity is meaningful. In other words, it is a RG flow invariant. Yeah, and yeah, and also if alpha cannot be erased by such beta, then you cannot do this. So you can't do this kind of gauging, because if this and this are not equal, and you cannot remove such difference by the redefinition of beta, then you cannot consistently define the gauge theory. So that will become that is the obstruction to gauging. Yes, thank you for asking. Yeah, I didn't explain.
Are there other questions? People can also just unmute and ask questions.
So I asked this question in the chat just now. For the
Would you speak it up? I mean, I don't know which question.
So so for the case of non-invertible operators, can we say that the quantum theory has a Z2 symmetry for each non-invertible line?
Yeah. So for non-invertible lines, okay. So for non-invertible lines, sorry, I should be clear that this is not this is not in general true. This is only for the group, I mean, only for the invertible lines. And
I see.
And so for non-invertible lines, yeah, there's no good way to phrase it in the conventional language. It's just non-invertible lines, and you have to use some math which is more general than the group, and that's usually called the fusion category. And so yeah, that's why I call it the category symmetry. And
I see. So the fusion of two lines with opposite orientation won't necessarily be a trivial line.
Yes. So what happens is that, yes, a good question. So yeah, what happens is that, yeah, there's always some of course you can always do this, like this is the trivial line, but there can be other line. This is I don't know, A and A bar, but there can be other line that starts from here. So such thing doesn't happen. This kind of thing doesn't happen for the group, right? You only have
right.
This kind of thing, but in general there is. And yeah, so in such case, yeah, we have to generate the notion of group, and yeah, and call the fusion category. Fusion category is for the 2D, and in higher dimensions recently, the Theo Johnson-Fry defined something called the fusion end category, higher category, and That should be, that is supposed to be the correct notion. But,
I see. So for example, one example of such a thing would be Wilson lines, because they sometimes have fusions of this sort.
Right. So yeah, one easy way to get such is that in 2D you gauge the non-abelian finite group. Then the Wilson lines of such gauge symmetry is yeah, like this. Yeah, that's one way. Yeah, another important example is the duality line of the Ising model. So there's a topological line corresponding to the Kramers-Wanier duality in the critical Ising model, and yeah, that's another example.
Thank you.
Yeah, thank you for asking.
Are there any other questions?
Guillermo had a question.
Yes, I have one question. So you said before that alpha is a map from 3 copies of the group to U1 subject to this pentagon identity. And I don't understand the last thing that you mentioned, how the classifying space of the group appears. I can see how this beta ambiguity more or less works, but not.
Yeah. So yeah, if I do redefine this junction by this number beta. Okay. So here, okay. So here I get from the left hand side, I get the beta of G1, G2. Yeah, so I mean I do the redefinition simultaneously. So from this junction I get the beta G1, G2, so G1, G2, and from this junction I get G1, G2 in this way, so G1, G2, G3. And
yes, so I mean, this part is not the problem that I have. I think that in the next page, when you write that this belongs to the H3 of the classifying space of the group with coefficients in U1, and I understand that you have to quotient by these beta things, but I don't understand how the classifying space of the group appears.
Oh, I haven't explained the classifying space. Here I'm just using this as a notation. So this is one way to define the group cohomology. And of course this group cohomology should be equal to the usual simple shell or whatever cohomology of the classifying space. I haven't, yeah. Here I just BG as just a notation. But yes, you can use explicit simple model of BG, the classifying space, such that it literally realize this kind of pentagon identity and this type of calculation. So yeah, there's such model of BG. Yeah, but here you should. Here I'm just using as a notation. Yeah. So sorry if it's confusing.
Thanks.
Are there any other questions? Okay, if not, let's thank Kantaro for the wonderful lecture, and we'll take a half-hour break, and then we'll have a lecture by Irene Valenzuela.
Great. Thank you. Thank you for listening.
Kantaro.
Thanks. So is the Zoom channel stay on forever?
Just
I think it will stay on for a continuous time from about 9 o'clock Eastern until like 4 o'clock or so. So people can also just hang out here and ask more questions.
Sure. Shall we stop the recording? So it's
we should probably stop the recording. Whoever started it.
Stop it. Stop it.
You know how to restart it, right? Or
and then I have to restart it. I don't think anything bad could happen by doing that.
Ivo, you will chair the next session, and you need to restart the recording.
Okay, so I'm going to stop it and see. Hopefully, things will not explode. Or pause it. I can pause it.
2014. Okay, we should have a T-shirt here. Yes.
Yeah.